Hello, my friends, and welcome back to another exciting module here in GSC 109 and the accompanying lab GSC 109L, also commonly known as General Physical Science, where we want to be able to take a look at the world around us and be able to take physical science concepts, specifically found in physics, and apply them. So that way we can learn about a variety of different topics that can inform us about the big picture of what is going on in the world around us. Now, as part of this class, I always like to open up with the phenomena. And I want to be able to share a phenomena with you that where we can apply this week's module and also topics that we have previously covered to learn more about this great dynamic phenomena. In a sumo wrestling match, the physics of collisions, gravity, momentum, and energy are essential to understanding how these wrestlers interact in competition. Here, we see top clips from the recent Kyushu Baso tournament, a promotion match for many of these dynamic wrestlers. And we can see physical science concepts at play, such as gravity. Gravity keeps the sumo wrestlers grounded and helps them maintain stability. The force of gravity, or their weight, some of these wrestlers approach around 600 pounds, is proportional to their mass, F equals mg. The heavier wrestler has more force pulling them down, giving them a natural advantage when it comes to resisting the pushes or being lifted off of the ground for elimination. Momentum plays a crucial role in the collisions between sumo wrestlers. Momentum is the product of mass and velocity, P equals mv. When a wrestler charges their opponent, they generate large amounts of momentum. Since sumo wrestlers have significant mass and even a modest speed, this results in a substantial momentum that must be countered by their opponent. Interestingly, the total momentum before and after collision is conserved according to the principle of conservation of momentum. So if a smaller wrestler moves quickly to charge at a larger opponent, their velocity can make up for the difference of their lower mass, giving them enough momentum to shift the larger wrestler towards the circle for elimination and win the match. Conversely, if the larger wrestler is moving, their mass actually gives them much more significant momentum, making it difficult for the smaller wrestler to resist. This week, we're also going to take a look at elastic and inelastic collisions. And we can see that in these matches. When two wrestlers collide, the type of collision they experience can be explained using Newtonian physics. If the collision is elastic, both wrestlers might bounce off each other, transferring momentum but retaining most of their kinetic energy. However, in sumo, most collisions are inelastic, meaning that the energy is not fully conserved in terms of kinetic motion because much of it is transferred into deforming their bodies and generating heat to eliminate the effects of the collisions. The wrestlers might grapple and try to reduce their opponent's momentum by using their body to absorb the impact, which can be the equivalent of a small car collision, which I think is a great way to compare this phenomena to one that you may or have seen or experienced and apply Newtonian physics. Now, speaking of energy, wrestlers use both kinetic energy that of motion and in displacement kinematics as they're charging at each other and displacing from one point to the next, but also potential energy stored due to their crouched starting position. When a wrestler charges forward, they're converting that energy stored into their legs into that kinetic energy. When they collide, some of that kinetic energy is transferred to their opponent, and then after that collision, the wrestlers often are trying to redirect and dissipate this energy, pushing their opponent's momentum against themselves. And we can confirm this with evidence by using Newton's third law of motion as a line of evidence to support all of these phenomena that we are experiencing and learning more about. Newton's third law states for every action there is an equal and opposite reaction. So when two sumos collide, the force one wrestler applies to the other is met with equal and opposite force. In these collisions, the ability to withstand and redirect the opponent's force is determined by the outcome of the match, or how efficiently can the wrestlers address gravity, momentum, and the energy from the collision. And I think this is a great way to think about this week's phenomena. Now we're back into our online digital classroom, and I want to be able to share with you basically the big picture of thematic section number 1, where we want to be able to learn more about physical science phenomena. And in this case, we're going to use motion and energy to tell the tale and relate all of the different little concepts we've encountered thus far. So I've actually pulled up what they call a mind map, and I love doing mind maps as a form of note-taking and keeping my mind and concepts organized. And so I highly recommend it. And if you want to learn more about this way of organizing notes, please reach out. But let's actually get started with the phenomena of motion and energy, because when we say look out the window, I actually can see the highway right here. I'm seeing some cars moving along, and it asked me the big question of how are those cars actually moving? And as part of science, we need to take a look at the scientific method. In most science classes, we teach it as a rigorous step-by-step process, but I flipped the script. I find that the scientific method is slowly becoming outdated because, well, we're in the world of artificial intelligence. Science is dramatically growing and changing every single day. And so let's think of it more like a recipe for, let's say a TV dinner or even a guide. But there's some good insights we can get from the scientific method. First, we can use it as a way to comprehend and actually make guesses about what's going on in that phenomena. You have your observation, you have your educated guess, the hypothesis. You can design experiments with independent and dependent variables, which can be very easy to map into many of these phenomena that we encounter in this course, and then be able to conclude it and converse about it using scientific awareness and literacy. And at the end of the day, I just want you to be a skeptic. Misinformation is very common, especially in science, and we can do small statistic tests, such as a t-test, to be able to confirm and deny that did we select the right variables? Are we interpreting our data correctly? And this is really good because it all comes into play with evidence. And evidence is best used as a way to prove your point. And back in the 1600s, you have Sir Isaac Newton, and he actually described the laws of motion. And these eventually became known as Newton's laws because he was taking observations from other scientists, realizing there's a common theme, and then subject them to the scientific method and be able to experiment and write down these laws, these strict definitions. And that's why we use them as a scaffolding topic, a segue topic, where we get to learn about the phenomena, which is going to be one-directional kinematics. Then we define what laws are at play, then go into two-directional kinematics. Now, when we take a look at the laws, we have the first law of inertia, law of acceleration, and then actions and reactions with their respective formulas. When we take a look at the first and second laws, we can, on my map, take a look at kinematics, displacement and movement, either horizontally in one direction or adding a vertical element in two-directional kinematics. When we take Newton's first law of kinematics and apply it, we find that in one-directional kinematics, in the absence of an external force, all objects will move at a constant velocity or remain at rest. For an example, if no friction or other forces are acting upon a car, on a straight road, it will continuously move at the same speed indefinitely. And that's where we get the term constant velocity. Then we have two-dimensional motion, and this will be more for projectiles. For instance, in horizontal motion remains constant, and that's due to inertia. While vertical motion is influenced by gravity, gravity is only affecting the vertical components. So horizontal, the motion's fine, but then we start to see changes in that vertical displacement. And it's going to be a uniform effect. When we take a look at Newton's law of acceleration, or the second law, and we can still apply it to kinematics. In one direction, the second law explains how velocity is generated, or acceleration. For example, when we look at the cars on the highway, a car accelerates on the straight road, and the forces applied to the car is determining how quickly that velocity is changing. But when we put like an 18-wheeler, it's going to need a lot more force to generate that same level of acceleration. And in two-dimensional kinematics, both components of motion in horizontal and vertical are subjected to the forces, and Newton's second law governs how these forces are generating that acceleration to allow for one-directional kinematics to happen. You start to see on how one-directional, two-dimensional start to interlock and play, and then we can use Newton's laws as a way to basically point at and say, this is why it's occurring, because this definition has evidence powering it. Now, when we go into Newton's laws, we can take a look at a concept called gravity. And in Newton's laws for gravity, we can use the first and second law, and that's why I have this gray bar connecting first, second, and third together. Because in the first law, without gravity, an object in motion will travel in a straight line in constant speed, of course. Gravity provides the external force and changes the object's direction and speed, and particularly for projectile motions. In second law, gravity is a constant acceleration. It's about 9.8 meters per second squared on Earth, meaning objects in free fall will actually increase their speed, their displacement. So what we can do is we can also make further connections by combining gravity into our kinematics. As according to the third law, we can be able to understand that because of vertical displacement, you still have the effects of gravity. We can then combine the three and gain more insights, such as momentum. And here is a equation that we'll be using this week, because momentum is just the product of mass and velocity. And kinematics helps us generate that velocity. And then collisions, such as our sumo wrestlers that we're going to be working on in lab this week, will be under the effects of both potential and kinetic energy as they collide, because they're also under the influence of momentum. And then this informs us that science is all around us in a nice, complete, holistic picture. And we can learn more about the phenomena by taking small components and lines of evidence to help paint this picture, and tell effectively a story in our thematic section of movement and changes in energy as it's being displaced under Newton's laws. As always, if you have any questions, feel free to reach out. You can get a hold of me during open office hours using video chat. You can send me an email or swing by my office. Thank you and have an excellent day on our planet Earth.